Hey there, this is a video for Chapter 6, Section 2. This section is very similar to the last section. It's short and you're basically doing the same thing but with a different formula. Pay attention to the new notation and make sure you understand how to read the table and do the calculator work and you should be fine. Alright, let's get started. Welcome to the lecture video for Chapter 6, Section 2, Confidence Intervals for the Mean where sigma is unknown. This section is very similar to the last section, except now we're dealing with situations where sigma is unknown. In this section, we're going to learn how to interpret the t-distribution and use a t-distribution table, and we're going to learn how to construct and understand confidence intervals for a population mean when sigma is not known. In real life, if the population mean is not known, then sigma, the population standard deviation, is probably not likely to be known either. So how do we construct confidence intervals for a population mean when this happens? Well, it turns out that when the population standard deviation, or sigma, is unknown, and the sample size is less than 30, if we know a random variable is approximately normally distributed, then it will follow a t-distribution. A t-distribution's values are defined by its ratio. X bar minus mu divided by this other ratio of the standard deviation of the sample divided by the square root of n. This is very similar to the standard formula for z-scores, remember? X minus mu divided by standard deviation, except this time the standard deviation is drawn from a very specific set of values. Similar to the last section, critical values for t are denoted by t sub c. Here are some properties of the t-distribution. The mean, median, and mode of the t-distribution are equal to 0. The t-distribution is bell-shaped and symmetric about the mean. The total area under a t-curve is 1, or 100%. Okay, so far these characteristics are very similar to the z-distribution, or standard normal curve. Now come some changes though. The tails in the t-distribution are thicker than those in the standard normal distribution due to the degrees of freedom. We're going to talk about those. With the t-distribution, we're really dealing with a family of curves, each determined by a parameter that is based on its sample size, called the degrees of freedom, or abbreviated df, which is the number of free choices left after a sample statistic has been calculated. Degrees of freedom is a sample size minus 1. Let's look at what this means. Think of it this way. When people are coming into a classroom and picking out chairs, every time someone sits down, there's one less free choice for the next person to pick from. That's how degrees of freedom are. After a sample statistic has been defined, there's one fewer degree of freedom. As the degrees increase, they get closer and closer to the standard normal distribution. Once we get to 30, we're close to the standard normal curve. So this blue curve is the standard normal curve, and a t-distribution curve that has 30 degrees of freedom would be very close to that curve. Whereas the one with only 5 or 2, like these other two you see, would be shallower and their tails would be thicker. The last property is that the standard deviation of the t-distribution varies with the sample size, but it is greater than 1. If you remember, the standard deviation of a z-distribution is 1, so this is a difference. Also, if you look at the table in the appendix, Table 5, you'll notice that there are some degrees missing, such as the numbers between 41 and 44. So the rule is that if the degree you're looking for a problem is not there, use the next closest one below it. This will give you a sufficiently conservative and high level of confidence number to work with. So how do we read these tables I just mentioned? Well, it's very similar to other tables we've worked with. Let's do this example. Find the critical table value for t sub c for a 95% confidence when the sample size is 15. Now remember, degree of freedom is n minus 1. So if our sample size is 15, we say 15 minus 1, or 14, is our degrees of freedom. So you first find the degrees of freedom along the left. See here we find 14. Then we find the confidence, or C value, of 0.95 at the top. Then we find where they intersect. For this one, it's 2.145. This is what it looks like on a graph. Very similar to what we did with z-distributions. At this point, you're probably wondering if there's a calculator shortcut like there was in the last section, and you'd be right. Yes, there is. It's called the inverse t function, and you use it almost the same way as the inverse norm function. To find t sub c, press the second second button, then the VARS button, then arrow down to or press the 4, the inverse T option. Press enter. Next, type your area. Again, this is similar to what you did for z-scores. We're talking about the small area to the left or right of the probable statistics, the tan area on the graph. Remember that you need to divide in half the area that's left after you subtract the larger area. So you put in the area in decimal form, for example, 0.025. Then press enter, then type in degrees of freedom. Remember that's n-1, so for example 14. Then press enter as many times as needed to calculate. Your result is the critical value, just like you got when you were figuring this with z sub c values. So let's go over this step by step of what to do for these. First, you want to verify that sigma is not known. If population standard deviation is known, you're going to use z distribution, not t distribution. So if sigma is not known, then you need to make sure that all the other conditions are there. Are the samples random? Is the population normally distributed, or is the sample size greater than or equal to 30? Next, if they aren't given to us, we need to find our sample statistics, like n and x bar and sample standard deviation. Third, now that we know we're employing the t distribution, we can take out some given information and find others like x bar, degrees of freedom, level of confidence, and the critical value t sub c. This is going to take some figuring. Fourth, we find the margin of error using the appropriate formula, E, in this case using all the sample information. Then lastly, we do exactly like we did in the last section. We subtract E from x bar to get our left bound and add to the x bar to get our upper bound or right bound, which will give us our confidence interval. Let's put these to the test, shall we? You randomly select 16 coffee shops and measure the temperature of the coffee sold at each one. The sample mean temperature is 160 degrees Fahrenheit, with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. Assume the temperatures are approximately normally distributed. So the very first thing we look at is whether or not sigma, population standard deviation, is known. They did not give it to us in this case. So we're going to ask the rest of the questions to see if we can use t distributions. The sample is random, and they told us the temperatures are normally distributed. So yes, we can use the t distribution. Next, we gather data. We have n equals 16, x bar equals 162, s or sample standard deviation equals 10, c or confidence level is 95% or 0.95, and degree of freedom is 15. We can use the table or our calculator to find that t sub c is 2.131. So you're not going to be given all of these numbers. Some of these you're going to have to figure out in the process of a problem. They may give you raw data and you have to find the x bar, and you may have to find t sub c using your calculator. But these are the numbers that you're going to end up with so that you can figure out the margin of error next. Okay, so next thing is to find margin of error. We need t sub c, s, and n for that formula. So we multiply 2.131 times 10, then divide by square root of 16, and we get about 5.3. That's our margin of error. Now we need to find our confidence interval. Again, you don't have to arrange it this way in your notes. Do whatever works for you. If we subtract E from x bar, we get 162 minus 5.3, which is 156.7 for our left endpoint, and add 162 plus 5.3, we get 167.3 for our right endpoint. Here's what it looks like on a number line and written as an inequality. And here's how we could word our conclusions correctly. With 95% confidence, you can say that the mean temperature of coffee sold is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Very good. Okay, now if you've been paying attention, you've already grasped this, but I want to point it out one more time just to make sure I'm reaching everybody. You need to make sure that for these types of problems, meaning confidence interval problems, you need to decide at the very beginning of your problem whether you'll be working with a t-distribution or a z-distribution. You need to ask yourself, is sigma known? Do I know the population standard deviation value? If yes, you ask questions to see if you want to go in the direction of a z-distribution like we did in section 1. If no, you ask questions like we did today to see if you want to go in the direction of a t-distribution. Let's do an example where that's the focus of the problem. You randomly select 25 newly constructed houses. The sample mean construction cost is $299,000, and the population standard deviation is $46,000. Assuming construction costs are normally distributed, should you use the normal distribution, the t-distribution, or neither to construct a 95% confidence interval for the population mean construction cost? Explain your reasoning. Okay, so something that's important no matter which direction we go is that either the population is normally distributed or the sample size is greater than or equal to 30. So let's check that first. Is the population normally distributed or is the sample size greater than or equal to 30? Yes, the population is normally distributed. Note that even though n is 25, and then that's less than 30, you can still use the standard normal distribution or the t-distribution because population is normally distributed. Next, is sigma known? Yes, they stated population standard deviation is $46,000. Okay, that makes the decision for us. Use the standard normal distribution or z-distribution. Let's do another problem just to make sure we've got all our ducks in a row. You randomly select 36 of the same model cars that were sold at a car dealership and determine the number of days each car sat on the dealership's lot before it was sold. The sample mean is 9.75 days, with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean number of days the car model sits on the dealership's lot. First question, is sigma known? No. That means we're possibly dealing with a t-distribution. Now, we saw up there that it did mention standard deviation, but it's talking about sample standard deviation. So we have the S value, not sigma. You want to make sure that you're very clear about that distinction. Okay, next question. Is the population normally distributed, or is the sample size greater than or equal to 30? No, they do not mention the population being normally distributed, but the sample size is larger than 30. It's 36, so we're good to go with that number. Now we look at whether or not the sample is random, which it was. So we can start gathering data and use the t-distribution. N equals 36, so our degrees of freedom will be 35. X bar will be 9.75. S is 2.39, and C is 0.99. I'll give you just a moment to see if you can come up with T sub C from this information. I'm hoping you got 2.724 for that. Good job. Now with all of this information, now find that formula for margin of error and find it for this problem. Pause the video to give yourself a minute. Here's what you should have gotten. Your T sub C value of 2.724 times sample standard deviation of 2.39 divided by the square root of the sample size of 36 is about 1.09. So that is our margin of error. Next, we construct our confidence interval from both sides. We subtract 1.09 from X bar to get 8.66 on the left and add it to get 10.84 on the right, and end up with a confidence interval of 8.66 to 10.84. And our conclusion is that with 99% confidence, you can say that the population mean number of days the car model sits on the dealership's lot is between 8.66 and 10.84. Okay, great work. That concludes section 2. Fantastic job. Go take a break. You have earned it. I'll talk to you on the next video.